The topic we're going to do today is something called linearization, and I think it's just one of the coolest, awesomest things in the world. Because if you want to find, let's say, like the square root of 7, or or whatever, what would you do? So you run to a calculator, you punch it in, and pow, you get your answer. But calculators weren't around forever. Even when I was a kid, we didn't really have calculators. Um, we had other machines, but not calculators like we have now. And certainly during the time of Isaac Newton and these guys, they didn't have calculators. So what did they do? Well, Isaac Newton came up, well, whoever, I think it was Isaac Newton, came up with this really ingenious way to calculate square roots or all kinds of things. A lot of squares are just, I'm mentioning square roots because I'm going to give an example during this video, but there are many, many, many things we could use this for, and I'll show you how it works. So let's just start from square one, and then we'll get to the punchline, which is calculating a square root. Anyway, we have a curve y equals f of x, and we draw a tangent, a line tangent to the curve, and it hits the curve at point A. So if you notice, the tangent line, when you're very close to the point of tangency, the tangent line is quite close to the curve. As you get further away, of course, each one goes on their own, their own path. But when so I can't really rely on that. But when I'm very close, to the point of tangency, I'm going to the line and the curve are very close to each other. Now, why is this important? How are we going to use this? Funny you should ask. The point of this is going to be that to get the equation of a line is easy, and to plug numbers into a line is easy to do, and that's going to be the whole secret. Again, let me just get through the mechanics of it, and then I'll show you how it works. So the equation of the tangent line is y equals f of a. F of a is the y value. This is basically the point slope formula. Normally it's y minus y1, but y1 is f of a1. And that normally equals m, but m is the f prime of a. It's the slope of the tangent. Times x minus a. Again, a being the point of tangency. And now I'm going to show you how to actually use this to find the square root of 2. So we're going to take the curve y equals square root of x. And here we go, y equals square root of x, and y prime equals 1 over 2 rad x. Now the curve y equals square root of x, it's kind of like a sideways, it's actually a sideways parabola, but just the top half of the sideways parabola. The bottom half was chopped off. Sorry about that. And that red line, of course, is the tangent line that we're going to try to find the equation of. So let's get some information here. First, we have to pick an a. So what we're going to do here is we're going to pick an a that's close to 2. That's a square. That's a perfect square. Now, 1 is a perfect square, which is close to 2. 4 is a perfect square, but that's still kind of far in this domain. So I want to find something even closer. So I'm going to be very smart. And I remember when I was in 8th grade, we had to memorize all the perfect squares. And I remember 14 squared was 196, which means 1.4 squared is going to be 1.96. So I'm going to let a equal 1.96. Well, if a is 1.96, f of a, which is the square root of a, is 1.4. So I like that because it just works out nice and evenly. F prime of a is 1 over 2 times rad x, which is 1 over 2 times 1.4, which is 1 over 2.8. So all these numbers are pretty easy to calculate. And I did not use by the way, I didn't use a calculator for any of this. All the stuff I was able to do by hand. That's kind of the point here, is that without calculators, we could still find these incredible square roots. Anyway, let's look at the equation that we're going to get from this. See, the equation we're going to get now, the equation we're going to use now, I'm going to say y is equal to f of a. F of a is 1.4, and f prime of a is 1 over 2.8, and I'm going to look now when x equals 2. That's what I want to find. I want to find what the y value is when x equals 2. I know the y value when x equals 1.96. The y value is going to be 1.4. I want to find the y value when x is equal to 2, because I want to find the square root of 2, or at least approximate it. Anyway, it's very easy to, these are very easy numbers to figure out, and I wound up getting that y is equal to 1.41428. Now, I want everyone to pause the video, go to your calculator, and plug in square root of 2 and see if we were close. Let's see if now, I'm not claiming this is exactly the square root of 2. I'm just saying that the point on the curve, the point on the straight line, when x equals 2 is going to be equal to this, and it's going to be pretty close to the curve when x equals 2. And that's really what I'm trying to do. I'm trying to approximate. Anyway, so pause your video, go to your calculator, and figure out and see what square root of 2 is. And if you did that, you found that square root of 2 is 1.41421 ... Isn't that incredible? Without a calculator, and again, this is not hard to do by hand, this calculation here. Without a calculator, we got the square root of 2 accurate to 4 decimal places. It doesn't diverge, it doesn't veer off until the 5th decimal place. But we got 4142, 4142. So without a calculator, we got square root of 2 to 4 decimal places. I just can't say how much that excites me. I guess I always find it fascinating when there are low-tech solutions to high-tech problems. In other words, normally we're used to using a calculator, which is a high-tech device, but here with just a little creativity and ingenuity, we got this answer to 4 decimal places. That's pretty darn accurate. I want to mention that notice that our approximation, which we got with the linearization, was 41428. And with the calculator, you see the actual value is 41421. Notice that our approximation was, which is very close, but it's a little bit higher than the true value, and that makes a lot of sense because you can see that from the picture, the tangent line is above the curve, so the tangent is a little bit higher than the curve. So it doesn't surprise me that that our approximation is very close, but it could have been very close. Slightly above, it could have been very close, slightly below. It doesn't surprise me that it's slightly above because the tangent is above the curve. Now, we're going to get to, in the next chapter, we're going to get to a whole topic on something called concave up and concave down. And because the curve is concave down, that's why the tangent is above, and that's why the linearization was slightly higher than the true value. And that is how we do that.